Welcome to the final section of Chapter 7. This one is on solving radical equations and inequalities. This video is only going to focus on solving equations that contain radicals. We'll talk about inequalities in class and do some examples, and there may be a subsequent video on that as well for your review purposes. So when we have a radical equation, the goal is very similar to some of the other equations that we've dealt with in the past that had a special operation. And the first step is going to be to get that operation by itself. So in this case, we're going to isolate the radical, because usually the variable that we want to get is inside the radical, so we have to at least get the radical itself by itself before we go any further. The next step is to try to figure out how we can eliminate the radical sign. And the way we do that is we take the whole equation and we raise it to the power that is equal to the index of the radical. That lets us eliminate the radical sign. Because if you think about it, if you've got something like the square root of 2, and you square that, well, that enables you to cancel the radical and the exponent and just give you the number 2. So we're going to be working with that property. And the same holds for higher radicals, too. The cube root of 2 cubed would also just be 2, because the cube and the cube root are inverse operations, and they cancel each other out. And then once you get rid of that radical, you solve the remaining equation. And then this is a biggie. This came up when we did absolute value equations, and it's going to come up again in this chapter. We need to check our solution, because sometimes we're going to get an answer that is extraneous. And remember, that means it works when you cancel out the radical, but back in the original problem, it doesn't make sense. So you have to make sure you're checking your final answers. And I'll be doing that as I model some of the ones on the video today. Okay, so here's a couple examples of some square root equations. We have the square root of x plus 2 plus 4 equals 7. So I want to isolate my radical first. So I want to get this x plus 2 to be all by itself. So if I subtract 4 from both sides of the equation, now I get just the square root of x plus 2 equals 3. All right, so I have an expression inside a radical. I can't get rid of anything else inside the radical until I eliminate the radical sign. And the way I'm going to do that is I'm going to square both sides of this equation, because that allows me now to cancel out both the radical and the exponent of 2 and have just x plus 2 equals 3 squared, which is 9. Then I'll subtract 2 from both sides, and I get x equals 7. All right, so before I circle my answer and get all happy, I'm going to check and see if I have an extraneous solution or not. See if 7 really works. So I'll replace the x with 7, and I'm going to check to see if I actually get the right equation. So the square root of 7 plus 2 is the same thing as the square root of 9. So I'll simplify that. The square root of 9 is 3. And when you add 4 to 3, you do get 7. So it does work. X plus 7 is a solution. Okay, let's look at the next one. This one's a little tougher because it's got more than one radical. Now, if you have more than one radical, you just have to isolate the first, or isolate one at a time. So we're going to have to do a little bit more work here to try to get rid of both radicals. So since I already have one radical isolated, I can jump right in and square both sides of this equation. Okay? The left side radical will cancel out, and I get x minus 12. The right side's a little bit trickier. I get the quantity of 2 minus root x, all of it squared. Remember, when you have a quantity, a binomial quantity that is squared, that is like saying 2 minus root x times itself. So to simplify this, I am going to have to FOIL. So my first is 4. My outer is negative 2 root x. My inner is another negative 2 root x. And my last is positive root x squared. Okay, we can clean that up a little bit. The root x's combine to get a negative 4 root x. And the square root of x squared is just x. All right? So now our goal is going to be to isolate that root x. So let's do that. So we'll do that. We'll move the x's over to the left. They cancel. Now I get negative 12 equals 4 minus 4 root x. I'll subtract the 4 over to the left. I get negative 16 equals negative 4 root x. Divide through by negative 4. and I get 4 equals the square root of x. Now that I have the second root isolated, I can square both sides a second time, and I get 16 equals x. But I'm not going to circle it yet. I'm going to check it. It's the square root of 16 minus 12. Is that equivalent to 2 minus the square root of 16? We'll work with the left-hand side first. 16 minus 12 is 4, and the square root of 4 is positive 2. The right-hand side, I get 2 minus 4, because the square root of 16 is 4. But 2 minus 4 is negative 2. They're not equivalent. 16 has to be rejected. It turns out that this equation has no solution, because the only answer that worked algebraically did not make sense for the original. Okay? Equations like these where you have multiple radicals is really, really, really important for you to check for extraneous solutions, because that's more often where we're going to see them. You should still check problems like the first one we did that had one radical, just to make sure you did everything right and just to make sure there wasn't anything that could be extraneous. But things like this, it's really important to do that. Okay? You have a few example problems now in your note sheet. Give those a try. We'll talk about them in class. When you're ready to move on to some higher indexed roots, pick up the video at this point. Okay, so let's talk about what happens when we have higher indexes and higher powers. The algebra is going to be exactly the same. So for the first one, I've got the cube root of 3y plus 1 plus 5 equals 0. Again, I'm going to isolate my radical. So I'll subtract 5 from both sides. Now I've got the cube root of 3y plus 1 equals negative 5. All right. Now I need to undo a cube root, so I'm going to raise the entire equation to the third power now. The cube root and the third power on the left disappear, and I get 3y plus 1 equals negative 125. Remember, the negative 5 is going to be in parentheses when I cube this. I'm cubing the number negative 5, so I get another negative back. Now I'll solve for y. Subtracting 1 gets me 3y equals negative 126. Dividing by 3 gets me y equals negative 42. And I will check this just to make sure. So the cube root of 3 times negative 42 plus 1 plus 5 equals 0. Well, does it? So the inside becomes the cube root of negative 126 plus 1, which is the cube root of negative 125. The cube root of negative 125 is negative 5. When you add the outside 5 to it, you do get 0, so I believe y equals negative 42 will work. Okay? Trying this second example now, we have a fourth root. Again, same tricks. Isolate the radical, and then we're going to raise the whole thing to the power of the index. So we have 7 times the fourth root of 5x plus 4 equals 14. Divide through by 7. You get the fourth root of 5x plus 4 equals 2. We raise that to the fourth power of both sides. 2 to the fourth power gets me 16. So 5x plus 4 equals 16. We'll subtract 4. 5x equals 12. X is going to equal 12 over 5. Embrace the potential for fractions. I'm going to go up to the top of my slide and do my check. So 7 times the fourth root of 5 times 12 over 5 plus 4 minus 4 on the outside. Is that 10? Well, let's see. It's 7 times the fourth root of 16, because the 5's cancel, so we get 12 plus 4, plus another 4 equals 10. Oh, not plus 4, sorry, minus 4. So the fourth root of 16 is 2. 7 times 2 is 14, minus the 4 does get me 10. This does check, so 12/5 will work. All right, you have a couple higher power examples now to try. Pause the video and do that for me, please. If you have any questions, feel free to ask them in class or rewatch these examples. Again, it's the same idea as the first slide, except now we're raising to the index, which is going to be greater than 2. All right, last but not least, it's back. Word problems using radical equations. All right, let's take a look at this. This is printed in your notes as well. The time t in seconds that it takes a pendulum to make a complete swing is modeled by the formula t equals 2 pi times the square root of L over g, where L is the length of the pendulum in feet, and g is the acceleration due to gravity, which is 32 feet per second squared. For those of you that take physics, you may know that already. In meters, it's 9.8, but we're going to use feet here in this problem. So it says, suppose a clockmaker wants to build a pendulum that takes 10 seconds. How long should the pendulum be to the nearest foot? All right, so let's start with our equation. We've got t equals 2 pi root L over g. What do we know? We know the time we want should be 10 seconds. And acceleration due to gravity is a constant. So g has to be 32. What we don't know is L. So let's plug in our known values. We get the equation 10 equals 2 pi times the square root of L over 32. And then that's what we want to solve for. That big L. Okay, so I want to isolate my square root. So this is 2 pi times a square root. So let's divide both sides by 2 pi. Okay? Now, at this point, you can go to your calculator if you'd like. But I'm going to wait a little bit for that. So I'm just going to leave it as 10 over 2 pi. You could also reduce it to be 5 over pi if you wanted. Equals the square root of L over 32. Now, this is the point where I'm going to go to my calculator, because I have to square both sides of this equation to get to that L over 32. Okay? And on my calculator, when I did 10 over 2 pi quantity squared, I get 2.553 equals L over 32. All right? Make sure when you do this on your calculator, you put parentheses around the 2 pi, because otherwise, the order of operations, it's going to do 10 divided by 2 first, and that's not what we have here. The whole 2 pi is in the denominator of that fraction. Okay? And of course, put parentheses around the whole thing to square the whole thing. Okay, now we've got to figure out what L is. So we have L divided by 32. So why don't we multiply both sides by 32 to just get it that L? And I'll go back to my calculator and do 2.553 times 32. And round it to the nearest foot, that's 81, which is a pretty long pendulum, but it will take 10 seconds based upon the math here. Which I guess makes sense if you think about pendulums like a grandfather clock, if anybody's seen one of those. That's not nearly as long as 81 feet, those pendulums, but it doesn't take 10 whole seconds to swing. It takes a much shorter period of time. Okay? So that's the answer. That would be a very large pendulum, but it would take 10 seconds to swing completely back and forth. You have another example like this using this exact same formula, just a different length of time that we want to solve for. So give that a try. Bring all these notes to class as well as any of your questions from this video. Thank you very much for watching, and I'll see you in class.